Welcome back. Today, we're going to look at transfer learning, which is a special topic because up to this point in time, we've created all our models from scratch. Turns out that a lot of the time, models are not created from scratch for production use. Instead, a model that has been trained by someone else can be picked up and modified to suit a particular application. Before we get to that, let's look at what we're going to cover for today. First video, we're going to introduce the ImageNet Large-Scale Visual Recognition Challenge. It's a challenge that we could say contributed a lot to the advances that we see in computer vision today. Second video, we're introducing an architecture called VGG16. This architecture came second place in 2014 for the ImageNet Large-Scale Visual Recognition Challenge. Over the years, we've seen various other architectures, such as AlexNet in 2012. We're going to look at VGGNet, because a lot of solutions get rolled out that are based on it. Third video, we're going to discuss state-of-the-art models, or SOTA, which are models that have come out in first place in the Visual Recognition Challenge. These models are usually available as pre-trained models in numerical libraries, like TensorFlow. Fourth, we're going to look at what you need to do to get your models to work in constrained devices, like mobile phones and Raspberry Pi devices. Finally, we're going to look at re-implementing pre-trained models, and how you can modify them to suit your use case. Before we get started, let's look at one solution to the assignment from Step 5. This assignment is a pretty straightforward time series. The data itself has different prices, like open and close, as well as high and low. You could choose to work with any of the columns. Our assignment solution shows a simple one-layer solution. Do go through the code, and then join us for the rest of the module. Let's look at the first topic from Step 6, introducing the ImageNet Large-Scale Visual Recognition Challenge. Let's look at some things that have contributed to the advances in the field of computer vision. The MNIST dataset is the first dataset that a lot of people that get an introduction to computer vision works with. This dataset is used for training both dense networks and CNNs. The dataset provides 70,000 handwritten images that were collected from the U.S. Postal Service. It's split into 60,000 training images and 10,000 validation images. In 1998, a new architecture called LeNet 5 became prominent for its classification accuracy of the MNIST dataset. We got this architecture up on screen. The images in the MNIST dataset are monochrome, so there's only one color channel and the images are 28 by 28 pixels. There are two convolution layers. The first has 6 filters. The second, 16. Both use 5x5 kernel and a stride of 1. Each convolution layer is followed by an average pooling layer. There are 2 hidden dense layers, and a final dense layer with 10 neurons for each one of the classes. By looking at the architecture, you could see the details of the trainable parameters. The question now is whether we could take this architecture and apply it to bigger problems, like images of cats and dogs. The ImageNet Large-Scale Visual Recognition Challenge is a task to classify about 14 million images into roughly 1,000 different categories. These images were not especially collected. Instead, most of these images were from the internet. All the images were colored. A number of researchers got interested in the challenge. These same people put in a lot of work. A lot of people applied dense models to the challenge. A new architecture called AlexNet was applied to the challenge in 2012. The paper is on screen now. The paper has Jeffrey Hinton as one of the authors. The team worked with 1.2 million images. The paper details the architecture. At that time, it took them 6 days to train the model using GPUs. Let's go back to the notebook and look at the implementation. The model was designed to accept an input image size of 224 by 224 pixels. This meant the images would capture enough detail without being too large. Recall that the number of pixels in the image affects the number of neurons in the input layer. Because these are color images, there are 3 times more pixels. Here's a summary of architecture. A convolution layer with an 11 by 11 kernel and 96 filters, followed by a normalization layer and then a max pooling. Second convolution layer with 256 filters, and a 5x5 kernel. followed by a normalization layer and max pooling. Then we have 3 consecutive convolution layers with different numbers of filters, but the same 3x3 kernel. Next comes max pooling layer and a flatten layer. Next, a dense layer with dropout, and another dense layer with dropout, followed by an output layer. The number of neurons in the output layer is the number of categories you would like to classify images into. The activation used here is softmax. This model has over 45 million parameters. That's going to be a lot of mathematical computations. The model makes use of rectified linear units to combat exploding and vanishing gradients, along with certain initializations. The bias was initialized to 1 in some layers, 0 in others. The weights were initialized with random normal distributions, with a mean of 0 and a standard deviation of 0.01. The weight initialization is called kernel initialization in this API. So how good is this architecture? Do we have better ones? Because this took 6 days to train, we're not going to train it in this course. If you have access to a GPU and maybe cloud resources, you could try to train the model.